While the world fixates on the interstellar Comet 3, I/Atlas, an even greater danger slipped by unnoticed. Just 10 days before its closest pass to Earth, a new comet, C/2025 R2, also known as SWAN, was detected, missed by every major planetary defense system until it had already looped past the Sun. This wasn't a minor oversight. The only reason we know about it at all is because an amateur astronomer caught what global detection networks did not. If an object this big can appear from the Sun's blind spot without warning, what else are we missing? This is why 3I/Atlas isn't coming for us. But what's arriving is far more terrifying. The next few minutes may change how safe you feel beneath the night sky. September 11th, 2025. Vladimir Bezugli sat at his computer scrolling through the latest SWAN instrument data from SOHO, a routine he had repeated countless times before. But this time, something caught his eye. In the Lyman alpha images, a ghostly smear of hydrogen glowed where nothing should have been. Bezugli leaned in, tracing the arc across successive frames. It wasn't a solar artifact or a routine outgassing. This was a comet, bright and unmistakable, hiding in plain sight near the Sun's glare. The timestamp on the file, 11:34 UTC. Bezugli's pulse quickened. He opened a new message, attaching the cropped images and coordinates, and sent them to the Minor Planet Center and a handful of colleagues. Within hours, the amateur networks buzzed. Confirmation requests, orbital calculations, speculation. By the next day, September 12th, ground-based telescopes in Chile had eyes on the object. The comet, now designated C/2025 R2 SWAN, was real and astonishingly bright, with a tail stretching 2 degrees across the sky. Bezugli's alert had turned a quiet data trawl into a global scramble. For a moment, the world's attention shifted from distant interstellar visitors to a threat that had been hiding just out of sight, waiting for someone to notice. The clock on first detection was now running, and it had started with a single, careful observer. SWAN's discovery of C/2025 R2 was not an act of cosmic vigilance, but a reminder of how our tools and procedures can leave us blind. The instrument wasn't designed to hunt for threats. Its job is to map hydrogen in the solar system, scanning the whole sky about 3 times a week. Each sweep takes a full day, and the data isn't available instantly. There's a lag of 2 to 4 days before anyone can even look for anomalies. By the time Vladimir Bezugli spotted the hydrogen cloud on September 11th, the comet had already passed perihelion a day earlier, skimming 0.504 astronomical units from the Sun. That means the object was at its most active, outgassing furiously and flooding space with hydrogen. SWAN could see the cloud, not the nucleus, so it took a comet in full eruption to register it all. This cadence, 3 images per week, each with a built-in delay, means a fast-moving object could slip through entirely. If R2 SWAN had been less active, or if its outburst came a few days earlier, even the hydrogen glow might have gone unnoticed. Ground-based telescopes and automated surveys couldn't help. Anything within about 30 degrees of the Sun is invisible to them, lost in the glare. The so-called Holacek effect kept the comet hidden for weeks, and only after it had survived its closest brush with the Sun did it emerge from the blind spot. SWAN's late notice wasn't a fluke. It was a symptom, a technical and procedural gap that leaves us vulnerable, not just to comets, but to anything that approaches from the direction of our own star. Around 15 to 20% of the sky is off-limits to our best ground-based telescopes, lost to the glare of the Sun. That blind spot isn't just a technical nuisance. It's a gaping hole in planetary defense, large enough for a city killer to slip through undetected. The Holacek effect, named after the 19th century astronomer who first described the problem, means anything sneaking in from the Sun's direction is practically invisible until it's well past perihelion. No amount of software can compensate for the simple fact that you can't see through daylight. The numbers sharpen the risk. NASA's Planetary Defense Coordination Office runs on a budget that barely cracks the tens of millions, less than what's spent on many single astrophysics missions. and a fraction of the cost of a Mars rover. Most of that money flows to established surveys like Pan-STARRS and Atlas, which are optimized for wide-field night sky patrols. But their reach ends abruptly at the solar exclusion zone. Objects like R2 Swan or the near-miss asteroid 2025 TF, which skimmed just 428 kilometers above Earth, remind us that these gaps aren't theoretical. They're real, and they're measured in missed warnings, not just missed science. Institutional silos deepen the problem. Solar physicists and planetary defense teams work in parallel, rarely sharing data or priorities. SWAN's hydrogen maps are archived for solar wind studies, not for threat detection. Even when a comet blazes to life in the blind spot, the delay between observation, processing, and human review can stretch to days. By the time an object is flagged, the window for meaningful response may have already closed. The system isn't broken. It's just not built for the threat that's most likely to catch us off guard. Online forums lit up within hours of the official confirmation. The first rumors broke through before the Minor Planet Center had even finalized the comet's designation. In the absence of clear details, speculation filled the void. Threads on X and Reddit exploded with theories. Some insisted R2 Swan was a government cover-up. Others claimed it was an alien probe. A few even suggested the timing was a distraction from global events. Screenshots of orbital diagrams, often cropped or misinterpreted, spread faster than any official update. Viral posts warned of an imminent impact, racking up tens of thousands of shares before astronomers could weigh in. Pressure mounted on agencies to respond. NASA's social media team scrambled to issue statements, clarifying that R2 Swan posed no danger and explaining the challenges of detecting sunward objects. But the lag between discovery, scientific verification, and public communication proved costly. Each hour of silence allowed new narratives to take root, some harmless, others corrosive. Conspiracy channels gained followers, amplifying the idea that scientists were withholding the truth. Even mainstream outlets struggled to keep up, often repeating unverified claims in the rush to report. The pattern is familiar. When official information arrives late, uncertainty multiplies. The slow cadence of scientific review, essential for accuracy, clashes with the viral speed of online rumor. In the end, the real cost isn't just confusion. It's a slow erosion of public trust, making it that much harder for experts to be heard when the next alert comes. The information vacuum surrounding R2 Swan turned a technical blind spot into a social one, exposing a vulnerability no telescope can fix. Artificial intelligence now scans the sky in ways no human team could match. Software combs through millions of images, flagging anomalies in real time, never tiring, never blinking. When a new object appears, these digital sentinels can trigger global alerts within minutes, much like the LIGO network does for gravitational waves, instantly notifying telescopes around the world to pivot and observe. The SOHO archives, once sifted by hand, are now mined by machine learning algorithms capable of spotting subtle patterns hidden in years of solar data. AI doesn't care about institutional boundaries or scientific silos. It simply follows the data wherever it leads. The result is a planetary defense network that operates at the speed of light, not bureaucracy, turning the world's telescopes into a single, coordinated, early warning system. Engineers and mission planners have already drawn up blueprints for a new class of solar sentinels. These telescopes would sit at the L1 Lagrange point, staring permanently into the solar blind zone with wide, unblinking eyes. The hardware is refreshingly simple. A 20-centimeter aperture paired with a detector covering an 8-degree field of view, snapping exposures every 15 minutes or less. No waiting for data downloads, no days-long lag. Every frame would be scanned by onboard software for anything moving against the solar backdrop: asteroids, comets, or the next unknown. The philosophy is always on, always watching. It's a lesson drawn not from theory, but from the missed warnings of the past. JWST, for all its power, never caught a supernova by accident. Its field of view is too narrow, its gaze too focused. What planetary defense needs is constant vigilance, not cosmic luck. On September 11, 2025, Comet C/2025 R2, also known as SWAN, was detected just 10 days before its closest approach, revealing a 15 to 20% blind spot in our current sky monitoring systems, as documented by SOHO data and confirmed by ground observations. This near miss was not due to a lack of technology, but the result of slow data processing, funding limitations, and institutional silos that left the sun-facing sky largely unguarded. As the documentary showed, this information vacuum fueled a surge in online speculation and conspiracy theories, undermining public trust. Some questions remain. How many objects have slipped by unnoticed? What risks are hidden in classified archives? Yet progress is underway. AI-driven scans and international alert networks now promise detection in minutes, and new telescope designs can finally watch the solar blind zone. The facts are clear. Our greatest cosmic risks often come from what we cannot or do not see. The universe offers no advance warnings. Responsibility for vigilance rests with us.